Welcome to section 11.3. We're going to discuss hyperbolas. And let's call this section 11.3, I don't know, Lunar Eclipse Edition. Handouts are on D2L, so you can follow along with those there, along with the links here as well. We're going to graph things that kind of look like ellipses in terms of their equation, except there's an important difference. I hope you see that important difference. It's right here. We've got a negative between these two things rather than a positive. That's a world of difference in terms of the graph. You go from having a graph which has two parabolas that face away from each other to an ellipse. So let's look at this a little bit and try and figure out some more about these types of graphs. First, a quick comment on where you'd see those shapes. Now, the hyperbola is one of our conic sections. That is the shapes that you get when you intersect a plane with two cones inverted tip to tip. I know it doesn't feel like a natural thing. This is what the graph is going to look like when you draw it for me, although the actual hyperbola is just the stuff that's in blue or kind of a light purple maybe. The rest is just some scaffolding. But as far as where you'd see the shape of a hyperbola, one place would be a nuclear cooling tower. Those have the shape of a hyperbola rotated around an axis. And of course, before we had GPS, we had this system called LORAN, which was a bunch of beacons set up around the Earth, and they emitted signals at a regular time. And you could calculate where your position was based on the intersection of a couple of branches of a hyperbola. Traveling faster than the speed of sound, you're going to leave behind a sonic boom. That boom will hit the ground in the shape of one branch of a hyperbola. Just kind of a nice cool shot of actually breaking the sound barrier. In architecture, you can see the shape of a hyperbola in Dulles Airport and in the Kobe Tower in Japan. So not quite as common as the shapes of a parabola, but definitely it's out there. Now, as far as the graph is concerned, one way to start getting a handle on the graph is to try and look at, what the intercepts are. So let's kind of do that real quick here. And if you're worried about keeping up with the notes here, I wouldn't stress about it right now. I want to get to a little point when I'm all done here. If we look for the x-intercepts, that would be by setting y equal to 0. If that term is 0, then you're just left with x squared over 4 equals 1. So x squared equals 4. X is plus or minus 2. So there would be our x-intercepts. When we play that same game for the y-intercepts, set x equal to 0, we find that we get y squared equals negative 16, so y is plus and minus 4i. So those aren't really points on our graph. We can't exactly graph imaginary numbers quite so easily. But they're still useful points. And let's see what they look like on the actual graph. So our intercepts that we found, the ones that actually did work, were right here and here at 2, 0, and 0, 2. Excuse me, 2, 0, and negative 2 and 0. But those other points are useful as well. Now, they were imaginary points, so let me kind of put them in there with a little circle there, where we're going to go up 4 and down 4 away from the center. And what that does is it allows us to draw a nice little box around our graph. So here, 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 and here. And that box is important because it's going to help us actually finish up our graph. So once you draw that, then you're going to draw the diagonals of the box, which have already been drawn in for you. So here and here. Then we've got to draw two parabolas that face away from each other. Now those parabolas are going to intersect our box here at these vertices. So this parabola, this hyperbola I should say, is going to open to the left and to the right. So its graph would look something like that. And over here, same kind of thing. Now the reason for this box, this rectangle, and the reason for these diagonals is because your hyperbola, which is in blue here, actually gets close to but never quite touches these lines, these asymptotes. So that's something I want you to use to help guide you when you draw your graph. Now remember, we used a couple of imaginary points in that. One of the things you'll see when you play around with this is there's a nice little correspondence in terms of our vertices of these points and the denominators here. So when we look back at our original equation, we realized that we could write this in a more productive way. I'll write that as x squared over 2 squared minus y squared over 4 squared equals 1. And then you can find those points by moving 2 to the left and 2 to the right. Up 4 and down 4 away from the center. And the center for all our hyperbolas in this section is going to be 0, 0. So 2 to the left, or 2 to the right, 2 to the left, up 2 and down 2. So these points here are 0, negative 4, and 0, 4 respectively. Great. Now there's a little bit of something else we got to pay attention to, and that is which term comes first. You could write your hyperbolas as x squared over a squared minus y squared over b squared, or we could flip the order of those. So if you have something like this, that is the x squared term is positive, this is going to open left and right. Opens left / right. If you have the y squared term goes first and is positive, then it's going to open up and down. So in this problem, if I would have had a plus y squared over 16 minus x squared over 4, then this thing would have been opening up and down as opposed to opening left and right. So nice. So there's our graph, and looking good on that one. There's one more thing that we'll tack on into this problem, that is the length of the transverse axis. And the transverse axis is the axis that goes through the center of your graph, and it links up both vertices of your graph. So in this case, the length of the transverse axis is the length from here to here, or a distance of 4. So the transverse axis has a length of 4. Nice, nice. You can follow along with the Desmos link up here. So scan it in with the QR code, and let me open that one up for ourselves here. Wrong one. There we go. Oh, there we go. So here's our hyperbola. I do want to see your rectangle, and there's one last thing I guess we could find, and that's the foci. So let's talk about that. To keep things absolutely confusing, in calculating the foci for hyperbolas, we're going to calculate c squared equals a squared plus b squared. Now, why do I say that's confusing? Well, it's confusing because when you're working with ellipses, this is a minus in here. With hyperbolas, it's a plus. You're going to find the foci inside each branch of the hyperbola, a distance of c away from the center. So in our case, that's going to be 2 squared plus 4 squared equals 20. So c equals the square root of 20. And that's where you're going to find your foci. So let's add those to our graph. And like I said, the foci should lie inside of each branch of the hyperbola. That's a distance of square root of 20. That's a distance of square root of 20. A little bit more than 4, almost 4.5 maybe. So, and I kind of got a little funny thing here. It says, look, Mom, I'm the internet. And a reminder that both foci should lie inside the vertices. Now, what if I screwed up the foci? Well, I'll let you click on that link yourself as you follow along here. You should see something that doesn't make sense. So keep in mind that the foci have to lie inside each branch of the hyperbola. It's easy to make a mistake because you mix this up with the formula for the foci for an ellipse, but if you tried to plot it, you'd quickly see that you made an error. Let's shut these down and continue with the graph for B. So the equation for B is this one, y squared minus x squared over 25 equals 1. So let's rewrite that a little bit. Example B, y squared minus x squared over 25 equals 1. So I chose this example for a couple reasons. The first of which is there's a little trick that you're going to want to employ when you rewrite this. Certainly, it's easy to do with this one over here. That's x squared over 5 squared. But for this one, first of all, write it as y squared over 1, and then realize that 1 and 1 squared are the same thing. The important thing to notice about this hyperbola to begin with is that you have a positive y squared term. So pause the video for a second. Test yourself. Which way is that going to open? All right. So this one's going to open up and down. And that's because the y squared term goes first. Now, as far as drawing the box that you need to enclose this, to enclose your center and then draw the hyperbola from there, how far are you going to move up and down? A distance of 1. And to the right and to the left of center, a distance of 5. So that gives you these 5 points that you're going to need in terms of, or these 4 points in terms of graphing your hyperbola. Now, only 2 of these are actual vertices. The vertices are these 2 above and below the center. Those are the vertices because this is going to open up and down. These other 2 are just here so that we can draw our hyperbola. So we can draw the rectangle that goes through all these points and then draw the diagonals through there. It's the diagonals that are really going to help you out because those are the ones that are going to help you draw your hyperbola, because your hyperbola is going to get close to but not quite touch those diagonals. So let's draw those in here. So there. When you draw the diagonals, they should pass exactly through the center. Now give yourself a little room for error because you're just doing this by hand, but it should be pretty close to center. So looking good there. This hyperbola is going to open up and down. It's going to touch at the vertices here and here. So like that, very wide opening parabola, and like that. Be careful when you draw your hyperbolas not to extend this past this rectangle. Doesn't go into the center, and also don't peel away from this. So that is, the hyperbola shouldn't just all of a sudden curve away from the asymptote. It gets ever closer. Now I am going to cut you some slack because we are drawing this by hand, but if it starts to egregiously look like a U as opposed to getting closer and closer to the asymptotes, I might be a little bit unhappy. One last thing to calculate, and that's our foci. Let's take a look at a better rendition of this. So that's your hyperbola. That's it. When you graph it for me on an exam, I am going to want to see this rectangle, and you got the diagonals in there as well. So that's roughly how it should look. Let's finish it up by calculating the foci. Now the foci are going to lie above and below here. They have to lie inside each branch of the hyperbola. So let's calculate c squared. C squared is going to equal a squared plus b squared. And in this particular case, that's going to be 1 squared plus 5 squared. So c squared equals 26. So c is going to be the square root of 26. Yeah, c is plus or minus the square root of 26, but as far as moving a distance away from the center, I'm going to move up the square root of 26 and down the square root of 26. So it should be a little bit over 5. So we'll just write 0 and negative square root of 26 and 0 and positive square root of 26. And that's your foci. So thing 1 and thing 2, or F1 and F2. Looking good. Looking good. Let's stick on this page and do one in a little bit of a different direction. It's this one, where you're given a little bit of information about a hyperbola, and you're asked to derive its equation. So we're actually going to work backwards in this one. And let me give you a chance to pause and think about this for a second. And that is, which way is the graph of this going to open? What equations are going to correspond? Is it going to correspond to the one on the left or the one on the right? Let's look back at our graph. X squared term first or y squared term first for this graph? All right, time for the big reveal. Did you get it right? Y squared over a squared minus x squared over b squared equals 1. You have to have a positive y squared term because it opens up and down. And I know a little bit more about my graph because it has a vertice at 0, 12. I know that that a underneath here has to be a 12, so that's 12 squared minus x squared over b squared equals 1. So, okay, I got that. I got to figure out a little something else in order to figure out what b squared is. The thing I haven't used yet is this piece of information. What does that tell me? What does that give me? Well, yeah, that's the foci. But what does it actually give me in terms of something that would be useful for solving for b? If you said that the foci lies at a distance of c away from the center, then good on you. C squared equals a squared plus b squared. So it's going to be 13 squared equals 12 squared plus b squared. 13 squared minus 12 squared equals b squared. 169 minus 144 is 25, so b equals 5. Okay, and that completes it. We've got y squared over 12 squared minus x squared over 5 squared equals 1. And that is our answer. Nice, nice. Now, in working with hyperbolas, years ago I found myself in need of a little trick to try and figure out the equations of the axis that run through this rectangle. And I found one that kind of works for me. You won't find it officially in any books, I don't think. But let's try and understand what's going on here. Sometimes I want the equation of the line that goes through here. And what I realized a bunch of years ago is if I take this general equation and somehow or another realize that, you know, let's cancel out that 1 and make it a 0. and then solve for y, then I get what I need, an equation for those diagonals, those asymptotes. You move the x squared over b squared term to the other side, take the square root on both sides. Well, I guess you could probably do one thing first, and that is multiply both sides by a squared. When you multiply both sides by a squared, you'll get y squared equals a squared x squared over b squared. And then you could take the square root. Once you take the square root, take plus or minus the square root. That's the equation of your asymptotes. So kind of a little bit of a shortcut in deriving those things, but it's nice to have this around when you have to work things in kind of a backwards direction. Keep in mind that the numerator of this ratio is going to be the denominator for y, and the denominator is just the denominator for x. So we'll use that coming up. In fact, we'll use it right now. We're going to try and find the equation of an asymptote that, or find the equation of a parabola that satisfies these given conditions. It has vertices here and here, so at 1 and 0 and at -1 and 0. Now let's stop for a second. If it has those vertices, what form of the parabola, or excuse me, the hyperbola are you looking at? The one on the left, I'll call that equation 1, one on the right, equation 2. So which one are you looking at? Which form are you going to write down in general for yourself? Hopefully you said the first one. So this has to open left and right, so it has to be of the form x squared over a squared minus y squared over b squared equals 1. And I actually know one of these distances, right? Because the distance from the center to that point right there to one of your vertices, that's going to be the value underneath x. So it's going to be x squared over 1 squared minus y squared over b squared equals 1. And we can actually get the other part of this kind of for free. Remember, this is the denominator for the x term, for the x squared term, but that is the denominator for the y squared term. So that's kind of cool. And another thing that's kind of cool is that I can just erase this. Hopefully you can too. And let's just squeeze in a 3 there. So that 3 is coming from the numerator there. 3 squared. Bam. And that's your equation. Looking good on that one. How are we doing here? Hanging tough with me so far? Okay, let's do one last one like this. We'll do it all the way through, including the graph, finding the foci, and the vertices and asymptotes. So let's come down to here. 9x squared minus 4y squared equals 36. The first thing what I would do is I would rewrite that. I would divide everything through by the 36. Keep in mind that generally speaking, when we're working with these types of conic sections, you're going to need a 1 on the right-hand side. So to get a 1 on the right-hand side, I'll divide everything here by 36. So let's see what that gives me. I'll have 9x squared over 36 minus 4y squared over 36 equals 36 over 36. So everything gets divided by 36. that's going to leave me with x squared over 4 minus y squared over 9 equals 1. Let's further rewrite it as x squared over 2 squared minus y squared over 3 squared equals 1. So perfect. That's what I wanted. I wanted to get something in that form. In the x direction, I got to go a distance of 2 from center, so 2 to the right and 2 to the left. And then up 2 and down 2, excuse me, up 3 and down 3. So up here and down here. Those are the 4 points. Now I just put hollow dots here. You don't have to follow my lead on that. Just to remind me that these are the vertices. These are just extra points so that I can draw the rectangle through these things. So let's do that part right here. Here. Okay, so there's our rectangle that runs through this. Now let's get the asymptotes as well. So the asymptotes are going to look like this. Diagonals of this rectangle. And the asymptotes meet nice and carefully right there in the center. All's looking good. This opens left and right because the x squared term is positive. So let's do that. Take care of that. So there's one branch. Let's graph the other one. So looking good. There's a couple things left that we'll find. Quick question. What's the length of the transverse axis? Ooh, see if you still remember that one. For now, let's figure out what c is. C squared is going to be 2 squared plus 3 squared. So 4 and 9 give you 13. C is going to be the square root of 13. And maybe it'd be convenient to have an approximate decimal value for yourself. So 13 raised to the 0.5 power, that's a quick way to get the square root, about 3.6. So if you wanted to put this on a graph and be reasonably accurate, about 3.6 and about negative 3.6. So somewhere in there. Now, as far as labeling it, it's going to be square root of 13 and 0. And negative square root of 13 and 0. But you can still put it in the right place. Let's see if we can't find the equation of the axis that runs through our center here as one last little step. Now the trick in that was to rewrite this with a 0. So let's see if we can't find the asymptotes. All right, x squared over 2 squared minus y squared over 3 squared equals 0. If I move that to the other side, then I get x squared over 2 squared equals y squared over 3 squared. Multiply both sides of this equation by 3 squared, I'll get 3 squared x squared over 2 squared equals y squared. And now let's take the square root on both sides. So square root here, square root here. On the left-hand side, let's not forget the plus or minus. The convenience here on the left-hand side is that everything's already squared. So I'll just take the square root by dropping the square and get plus or minus 3/2 x equals y. 3x over 2 equals y. Beautiful. If you actually looked at this kind of closely, you'd see that there's another way you can get that one. Our equation of a line through the center has to have the form y equals mx. The b part is 0, right? Because you're going through the origin. So we can ignore the b. Let's do that. Now, m is the rise over the run. That's our slope. If you look, we go up a distance of 3 and to the right 2, so 3 over 2. That's the equation of the line. Y equals 3 over 2 times x. In the other direction, it's the same thing, it's just you're going down, so you have a rise of -3, you'd end up with the -3 over 2. Okay, did you get the length of the transverse axis? The transverse axis has a length of 4 again, from -2 to 2. Okay. Hopefully you have fun with your Monday, your Eclipse day, whatever you choose to do. Good luck and see ya.